Hello my dear friends, this is one new video on electrostatics. Hope all of you are doing fine in this difficult period, keeping yourself safe. So today in this video I am going to discuss about continuous distribution of charges instead of the discrete one like Q1, Q2, Q3 up to Qn. Suppose we consider on the surface of a conductor a very small area. Such small area are said to be the elemental one, we can say it, and there are a group of charges. The distance between each charges in the group is very small and the groups are also closely spaced. In this scenario we can say that we have continuous distribution of charges which is distributed along some line or over some surface or throughout the volume. So let's discuss on continuous distribution of charges. Suppose this is a line over which there is charges spaced apart. So we consider some elemental line area of dl, and the position vector of the line area line dl from some arbitrary origin is small r vector, and we are trying to calculate at point P the electric field. So the distance between dl and the point P is r prime, and the position vector of the point P from some origin O is capital R. So we can write r vector, capital R vector, is equal to small r vector plus r prime vector. So the point P is called the field point and the source point is the elemental area dl or the elemental surface ds or elemental volume dv. So the source coordinate is given by small r and the field coordinate is capital R, and we can write that both the lambda, sigma and rho. So what is this lambda, sigma and rho? So lambda is defined as lambda is a function of its position vector, which is small r, is a charge per unit length, so it is called linear charge density. Similarly, sigma is charge per unit surface area, so it is called surface charge density, and also the rho is equal to dq dv is equal to volume charge density, and the unit of rho is coulomb per meter cube, the unit of sigma is coulomb per meter square, and the lambda has the unit of coulomb per meter. So we can see that the lambda, sigma, rho vary as a function of r. So suppose we consider some elemental volume here dv. The position vector of the volume dv is small r vector from some arbitrary origin O, and we are trying to calculate the electric field at point P, which has the position vector of r prime vector from the dv, and the position vector of the point P from O is r vector is equal to r plus r prime like before. So due to some elemental volume delta V, we can consider the electric field, what it will be at point P. Electric field, we all know that it is a vector quantity, so delta E is a function of vector. So its position vector capital R is equal to 1 by 4 pi epsilon naught times rho r, rho is a function of small r, times delta V divided by r prime square times r prime cap. So this is r prime. So we can consider some elemental volume here. So for the whole body, if we trying to calculate the electric field at the point P, so we need to sum up all such delta V elemental volume. So that is, we can write that E is a function of capital R is equal to 1 by 4 pi epsilon naught times the sum over all such delta V we need to sum. What is we need to sum? That is rho function of R times delta V. So rho R times delta V is the elemental volume that is there, elemental charge that is contained in the volume delta V, divided by r prime square times r prime cap. So in the limiting case where delta V tends to 0, so what we can do, we can sum up, we can replace this summation by some integral. So E is a function of capital R is equal to 1 by, for line charge density we can write 1 by 4 pi epsilon naught. This is the line integral of lambda is a function of r times dl, so this is the charge contained, divided by r prime square times r prime cap. For the surface we can write 1 by 4 pi epsilon naught, this is surface integral, sigma which is a function of small r times ds divided by r prime square times r prime cap, and for the volume we can write that is equal to 1 by 4 pi epsilon naught. This is the volume integral of rho, which is a function of its position, this is small r, times dv. So rho r times dv is the charge contained in the elemental volume dv. So if we integrate over the whole volume, we can get the electric field due to the whole body divided by r prime square times r prime cap, and we find it from the Coulomb's law and from the superposition principle. So far we can know that I have already discussed on the continuous distribution of charges and how the electric field expression looks like for such distribution of charges, we can see from here. And also we have got to know about the electric field and understood the behavior of the electric field lines for the point charges. So we have already discussed that the electric field means the number of field lines per unit area perpendicular to some surface, which is some imaginary surface. And what is the electric flux? Electric flux means that the total number of field lines passing through some given area perpendicularly. So electric fields, again I am speaking that electric fields is the total number of field lines passing perpendicularly per unit area, and the electric flux is given that in some certain amount of area how much electric field of lines is penetrating. So suppose we need to calculate the electric flux. So for that, we need to calculate the electric flux for some specific area of surface. So for that we need to describe the Gauss's law. So what is this? Suppose in this point a q charge is located, which is plus q, having charge plus q. So we considered some surface, imaginary surface here, some sphere here in 3D, some sphere here having the radius r, and the center is at the position of q. So the electric field will be, we know that the electric field will be homogeneous in everywhere from the point q, plus q, and it will be directed outwards. So we can say that this is the direction of the electric field, and on the surface of the sphere, if we take some elemental area, the normal of the surface will be at the same direction of the electric field, and we can take the small area as like that delta S vector is equal to its magnitude, delta S vector magnitude modulus of delta S times n cap. So the Gauss's law states that the net flux through any closed surface which is surrounding a charge, that is, we can say that the q enclosed is given by, so this is the closed surface integral of E vector dot ds is equal to q enclosed divided by epsilon naught. So we can write that the surface integral is independent of the shape of the surface. So what type of shape we are considering around the charge q, and the surface must be a closed one, and the surface must enclose the charge q. So it is what kind of surface we are considering? So it is independent of the shape of the surface. So we will get back to the proof of the Gauss's law. So the flux through an elemental area of delta S, what is this? Delta phi, we can write it E dot ds. So from this diagram we can see that from this point q at some distance r, we can write the electric field as that q by 4 pi epsilon naught, it's times r square times r cap dot delta S vector, we can write it as delta S of modulus times n cap. So we consider the Gaussian surface to be a sphere from some generality where the charge q is located at its center. So the direction, as I have already told you, that the direction of the electric field and the surface and the normal of the surface is in the same direction, so that the theta value is equal to 0 degree. So it becomes q delta S divided by 4 pi epsilon naught r square r cap dot n cap, and the angle between them is 0 degree. So it is q delta S divided by 4 pi epsilon naught r square. So the total flux coming out from the entire closed surface of sphere, we need to calculate this closed surface integral, that is E dot delta S closed surface integral is equal to closed surface integral of q delta S divided by 4 pi epsilon naught r square is equal to q by 4 pi epsilon naught r square. This is the closed surface integral of delta S. So what it will be, the closed surface integral of delta S, we know that the closed surface integral of delta S, it means we have already considered that the Gaussian surface to be a sphere one. So the closed surface integral means the upper surface of the sphere, that is 4 pi r square. So it becomes the closed surface integral of E dot ds is equal to q by 4 pi epsilon naught times q by 4 pi epsilon naught r square times 4 pi r square. This is the upper surface of the sphere, the imaginary sphere, the Gaussian surface, is equal to q enclosed divided by epsilon naught. So this is the proof of the Gauss's law. So what is the conclusions that we are getting from the Gauss's law? Is that suppose at that point the plus q charge is there, and I have drawn three imaginary surfaces. One is S1, another one is S2, another one is S3. So you can see, students, that only S2 is the sphere and the rest S1 and S3 is of some arbitrary shape. So you can see that only S2 is spherical, but flux coming from other two surfaces S1 and S3 are also the same. So it is independent of the shape of the surface. I have already told. All such closed surfaces enclosing one charge is called the Gaussian surface. So it is already discussed. The term Q enclosed, it means that sum of all the charges enclosed by the surface. So if the charge is distributed, we need to add up all the enclosed charges inside. And also the fourth point, what it will be, the electric flux through any closed surface that surrounds no charge, that will be 0. So suppose in this diagram you can see that I consider the electric field to be in this direction, and I consider some imaginary cylindrical surface here, and the axis of the cylinder is in the parallel direction of the electric field. So suppose in this direction, in the surface 1, which is a flat surface, this is the surface 3, which is also the flat surface, and the surface 2 is indicating here, which is the curved one. So for the two flat surfaces, we can write that the normal of the surface and the electric field, the angle is for the surface number 1, it is theta is equal to 0 degree, and for the surface number 3, the theta is equal to 180 degree, and for the surface number 2, the normal of the surface and the direction of the electric field is at 90 degree. So we try to calculate the closed surface integral of the E dot ds. So what it will be for the surface number 1, E dot n cap ds, plus surface number 2, this is not the closed surface integral, this is only the surface integral. So if I add these three, it becomes closed surface integral. So you will try to remember this. So for the surface number 1, this is the surface integral E dot n cap ds, that is for theta is equal to 0 degree, plus for the surface number 2, which is the curved one, E dot n cap ds, theta is equal to 90 degree, and for the surface number 3, which is also the flat one, E dot n cap ds, theta is equal to 180 degree. So for this one and this one, you can see this is EA and this is minus EA, and as this one is theta is equal to 90 degree, so it becomes 0. So we can see that the closed surface integral of E dot ds becomes 0. It means that in the right hand side we can see this is Q enclosed by epsilon naught. So if the left hand side is 0, it means that the right hand side also is 0. It means that the Q enclosed is 0. So it does not include any charge. So for the fifth point, we can discuss that when the system has some symmetry, it is much easier to calculate the electrostatic field using Gauss's law. So what is this? We can say that we need to choose some appropriate Gaussian surface. Like an isolated point charge, we can say that it has the spherical symmetry, or some infinite point of charge, we can say that it has the cylindrical symmetry. Thus the surface calculation, it's easier to find the angle between the electric field and also to the normal of the surface. So the surface calculation is more important in the Gauss's law. So now up to now I have discussed on the Gauss's law. So now let's try to calculate one of some application of the Gauss's law. We will now see one of the application of the Gauss's law. So the field due to an infinitely long straight uniformly charged wire. So suppose from the figure you can see this is the uniformly long charged wire. This tends to infinity in the downward direction. The direction of the electric field radially outward for charge density lambda greater than 0. If the wire carries some positive charge, so for the positive charge the electric field will be directed in this direction, you can see from the figure. And if the charge is negative, so it will be in the inward side. So what I have considered that I take the wire as the axis of the perpendicular cylinder of length L. I put the wire on the imaginary axis of the cylinder of the radius r. So we are trying to calculate the electric field at a distance r from this infinitely long straight wire. So this is the length L of the cylinder, and we can see for the curved surface the electric field and the normal to the surface is the angle between them is theta is equal to 0 degree. And for the two flat surfaces we can see that the normal of the surface and the electric field is at 90 degree direction. So from the Gauss's law we can see that the closed surface integral E dot ds, it contains three different terms. So 2 for the flat surface and 1 for the curved surface. So for the flat surface I have told you that the direction of the electric field and the normal to the surface is at 90 degree. So it becomes 0 because cos 90 degree is equal to 0. And for the curved one it has some value, finite value. So for the curved one the surface integral becomes E ds. So it means surface integral of ds, it means the surface area. So E times the curved area of the cylinder. So what is the curved area of the cylinder? We can write it that the Q enclosed. What is Q enclosed? So I consider that the line charge density is lambda. It means that the charge per unit length is lambda. So I took the length of the cylinder to be L. So in the length of L, the amount of charge that will be Q enclosed, that is lambda times L. And also the curved area of the cylinder is 2 pi RL. So in the left hand side, this is line surface integral of EDS, that is the curved surface. So E times 2 pi RL, the curved area of the cylinder, is equal to, from the Gauss's law we can find in the right hand side, this is Q enclosed. Q enclosed means this is lambda L. So lambda L divided by epsilon naught. So what we get, the value of E is equal to lambda by 2 pi epsilon naught R. And it directs in the same direction of the normal to the surface, or in the n cap direction. So in the vector form we can write it that E vector is equal to lambda by 2 pi epsilon naught R times n cap. So the length of the rod is infinite, and it's important to ignore the end effects. So what is the end effect? End effects means, so we choose that the length of the rod to be infinite. So if we don't take this, take this assumption, so there will be some effect from this. If this is a finite rod, so there will be some effect come from this to end. So friends, I am concluding my today's discussion here. If you have any kind of confusion, don't hesitate to let me know in this video's comment box. Stay tuned and keep supporting us. Thank you.